Hello, my curious friend, and a very warm welcome to Deep Field. Tonight, we are going to journey into the very heart of the stars, those ancient cosmic furnaces that forged every single atom in your body, every molecule of the air you are breathing right now, every speck of dust that has ever settled on the palm of your hand. It is a story about where things come from, in the most profound sense that question can hold, and I promise to try and keep the subject from being so dazzling that it steals your sleep tonight. But before we set off into this blazing universe, I would love to know in the comments which corner of the world you are listening to me from right now, and if laziness has already arrived first, just leave a simple hello. That small gesture tells YouTube that our space is welcoming, and it helps us bring more curious minds to relax with us. If you enjoy our journeys through the cosmos and science, please leave a like and consider subscribing. And for those of you who are already part of our community, who return here every night seeking a slightly gentler sleep, my deepest and most heartfelt thanks. Now, wherever you are, find a truly comfortable position. If sleep arrives before the end, accept the invitation with joy. Let us begin. There is a moment, perhaps you have experienced it without realizing, when you look at your own hand in the daylight and simply cannot fathom where it came from. Not in the biological sense, not in the years of growth and cells multiplying, but in a sense prior to all of that, something quieter and far stranger. Where did the iron coursing through your blood right now, as you lie down and breathe, come from? Where did the calcium in your bones come from, the carbon in your skin, the oxygen entering your lungs at this exact instant and dissolving into you as if it had always belonged to your body? Because in a way, it always has. The answer to these questions is not on Earth. It is not in any laboratory, in any factory, in any geological process happening beneath our feet. The answer lies in the stars, and this is not a poetic metaphor. It is the most rigorous and well-documented result of decades of physics, astronomy, and nuclear chemistry. Every element that makes up your body, with the exception of a minuscule amount of hydrogen that has existed since almost the very beginning of everything, was created inside a star. It was forged in temperatures and pressures that the human mind cannot easily visualize, and then it was hurled into space, traveling for millions of years, meeting other fragments from other stellar furnaces, and slowly, patiently, forming the solar system, forming the Earth, forming you. What you just heard deserves a moment of silence to settle in. Because the natural tendency when we encounter a statement like this is to let it slide across the surface of the mind without truly landing. We hear that we are made of stars quite often, in songs, in motivational quotes, in documentaries. But there is a vast difference between hearing that phrase as a beautiful ornament and truly understanding the physical process behind it. And understanding that process is what we will do tonight, calmly, deeply, and without rushing. But let us start at the beginning, or at what approximates a beginning in this story that has no easy starting point to pinpoint. Think of the universe just after what physicists call the Big Bang, that primordial instant of incomprehensible density and temperature. In the first minutes of this nascent universe, the temperature was so high that even atoms could not exist as we know them. What existed was a soup of fundamental particles, free protons and neutrons, moving at immense speeds, constantly colliding, unable to bind into anything more complex because any union would be immediately torn apart by the brutal heat of the environment. As the universe expanded, it cooled, and in a span of just a few minutes after the beginning, the temperature dropped enough for protons and neutrons to start binding and staying bound. This period, which cosmologists call primordial nucleosynthesis, produced the simplest elements in the universe, mainly hydrogen, which is simply a solitary proton with an electron orbiting it, and a smaller amount of helium, which has 2 protons and 2 neutrons in its nucleus, and minuscule amounts of lithium and beryllium. That was it. These were the ingredients the young universe had to work with. Now, if you look at the periodic table of elements, you will see it contains 92 natural elements, from hydrogen to uranium. The primordial universe produced only the first 3, with negligible amounts of the others. What happened to the other 89? Where did the carbon, nitrogen, oxygen, silicon, iron, gold, lead, and uranium come from? Where did everything that makes the world we know, everything that makes life possible, everything that makes you who you are, come from? The answer, as you already know, is the stars. But stars are not simply balls of fire floating in space, and this is one of the first misconceptions we need to dispel tonight. When we look at a star in the sky and realize that even the sun is so distant its light takes about 8 minutes to reach us, we tend to imagine it as something remote and abstract, a point of light without texture or depth. But a star is one of the most complex and dynamic structures nature produces. It is a constant battlefield between opposing forces of unimaginable magnitude, and it is in this tension, this precarious balance between collapse and explosion, that the elements are born. To understand how elements are created, we first need to understand what a star is like on the inside. And the best way to start is with the most familiar one of all, the one that lit up your day today and plunged the sky into orange and pink before you went to bed: the sun. The sun is a sphere of plasma, which is the 4th state of matter, a gas so hot that electrons have been stripped from their atoms and float freely. This sphere has a diameter of approximately 1,390,000 kilometers. To put this in perspective with something more tangible, if the sun were a basketball, the Earth would be a grain of rice about 26 meters away. And even so, the sun is classified as a yellow dwarf, a medium-sized star in the context of the cosmos. There are stars 1,000 times larger, stars whose diameter would make the sun look like a microscopic dot. At the center of the sun, in what astronomers call the solar core, the conditions are extreme in a way we need to try and visualize carefully. The temperature in this central region is about 15 million degrees Celsius. Not 15,000, not 15 million degrees like a common flame that burns at a few hundred degrees, but 15 million. The pressure in this region is so intense that it is 250 billion times greater than the atmospheric pressure you feel on your body right now as you lie down. This pressure is the result of the weight of all the solar mass above pressing down toward the center. Layers and layers of plasma compressing the core as if the entire universe were trying to crush this central point. Under these conditions, something extraordinary happens. Hydrogen nuclei, which are simply protons, are forced so close together that they manage to overcome the electrical repulsion that would normally keep positively charged particles apart. Under normal conditions, 2 protons would never spontaneously fuse, because like charges repel, and this repulsion grows exponentially the closer they get. It is like trying to push the positive poles of two very strong magnets together. You feel the resistance increase, and you would need an enormous force to overcome it. But in the solar core, the temperature and pressure are so extreme that the protons move with enough kinetic energy and are so compressed against each other that the strong nuclear force, that fundamental force that acts at very short distances and is more powerful than electrical repulsion when particles are close enough, manages to take over. And when this happens, the protons fuse. This process is called nuclear fusion. Nuclear fusion is the most fundamental mechanism for understanding everything we will explore on this journey. It is the engine that makes stars shine, and it is the process by which heavier elements are built from lighter ones. It is worth letting your mind rest on this concept for a moment, because it seems simple on the surface but carries an almost inexhaustible depth. When two nuclei fuse to form a larger nucleus, the product of that fusion has a slightly smaller mass than the sum of the masses of the two original nuclei. That tiny piece of mass that disappeared was not destroyed. It was converted into energy, according to the most famous equation in physics, the one that says energy equals mass multiplied by the square of the speed of light. The speed of light is roughly 300,000 kilometers per second. Squaring that number produces a value of astronomical proportions, and that is why even a minuscule amount of converted mass produces a colossal amount of energy. In the Sun, approximately 600 million tons of hydrogen are converted into helium every second. Of this process, about 4 million tons of mass are transformed purely and simply into energy. This energy is what warms the earth, what made your food grow, what drove the winds that rustled the leaves outside your window today. And it all begins with the fusion of hydrogen nuclei in the silent, incandescent heart of a star. But there is something deeply counterintuitive here, and this is one of the points where stellar physics surprises those encountering it for the first time. Nuclear fusion in the solar core, despite all that extreme temperature and pressure, is actually a relatively slow process. The energy density in the Sun's core per cubic centimeter is comparable to the energy density produced by your own body through metabolism. A human being generates metabolic heat per unit volume on a similar scale to the solar core. What makes the Sun so luminous is not that every cubic centimeter of its core is an inferno of energy production, but rather that the Sun has an immensely larger volume than any living creature, and all this slowly produced energy in each centimeter adds up to impressive quantities. This leads us to a myth worth dispelling carefully. Many people imagine the Sun as something continuously exploding from the inside out, like an atomic bomb in slow motion. But the Sun is not exploding, and understanding why it is not is fundamental to comprehending how stars function as element factories. The Sun is in equilibrium, in a state physicists call hydrostatic equilibrium. Gravity pulls all the solar mass inward toward the center. The pressure created by the heat of nuclear fusion pushes everything outward. These two forces balance each other with extraordinary precision, and it is this balance that has kept the Sun stable for about 4.5 billion years, and will keep it stable for a few more billion years into the future. Picture this: a ball of plasma nearly the size of a planet being compressed from all sides by the gravity of its own mass, and at the same time inflated from within by the immense heat generated by the fusion of atoms at its center. It neither collapses nor explodes. It simply shines, with a constancy that no human-made object has ever matched. This stability, this silent balance between titanic forces, is what gives stars enough time to cook the elements and build the chemical complexity the universe needed to produce planets, oceans, and living beings. Now, the Sun is made mostly of hydrogen, about 74% of its total mass, and helium, about 24%. The remaining 2% comprises all the other elements, those inherited from older stars that existed before the Sun was born. This composition is not special. It is typical for stars of its generation. The young universe was almost entirely hydrogen and helium, and the first stars formed were made almost exclusively of these two elements. These primitive stars were the first furnaces, the first laboratories where nuclear alchemy would begin building the more complex blocks of matter. But before we delve into the story of the first stars and how they built the first heavy elements, we need to have the stage where all this happens well established, which are the stars themselves in all their diversity. Because stars are not all the same, they vary enormously in mass, temperature, luminosity, and lifespan, and this variation has direct consequences on which elements each type of star is capable of creating. A very massive star, dozens of times more massive than the Sun, has a hotter and denser core, and can fuse progressively heavier elements until it reaches a limit that has catastrophic and magnificent consequences for the entire cosmos. The size of a star determines its life trajectory almost entirely. Stars less massive than the Sun live for tens or hundreds of billions of years, burning their hydrogen with extraordinary parsimony. Stars much more massive than the Sun live for only a few million years, burning their fuel with an intensity that drastically shortens their existence. And it is exactly this accelerated consumption that leads these giant stars to central temperatures and densities sufficient to forge the heaviest elements the cosmos knows. There is a proportion here that the human mind loves when it finds it, because it reveals a deep symmetry in the workings of nature. The more intense and brilliant a star's life is, the shorter it is. And the shorter the life, the more dramatic and fertile the end. It is as if nature had established a bargain. The stars that live most intensely are the ones that contribute most to enriching the cosmos with new elements. Long-lived, tranquil stars build elements with patience. But it is the stars that live fast and die young that deliver the rarest and heaviest elements to the universe. So, as you let your eyes grow heavier and your breathing slow down, hold on to this image. A star is not just a source of light. It is a transformation machine, a place where the simplest ingredients the universe produced at its birth are gradually, patiently, and sometimes violently transformed into something more complex. It is a factory that runs for millions or billions of years before opening its doors and distributing its products across space. And the question that will hover silently as you fall asleep tonight, the question we will open in the next step of this journey, is this: where does the energy that fuels these furnaces for so long come from? What keeps them lit in the cold void of interstellar space? And what happens when that energy begins to run out, when the ingredients become scarce, when the balance begins to tremble? There is a tension at the center of every star that never rests. It is not the tension of a contracted muscle or the tension of a rope about to snap, but something much quieter and much older. It is the tension between two forces looking at each other across time, neither capable of definitively winning, neither willing to yield completely. And it is exactly this stalemate that keeps the sun lit while you sleep, that kept the suns before ours shining for eons before they exploded and scattered their gifts across the space that would eventually become you. To understand where this energy comes from, one must first forget the idea of fire. The fire we know, the fire that warms, the fire that dances in hearths and roasted the meat of our ancestors for hundreds of thousands of years. That fire is a chemical process. It breaks bonds between atoms and releases the energy stored in those bonds. But the sun does not have enough chemical fuel to last even 1,000,000 years using that kind of process. A scientist named Hermann von Helmholtz in the 19th century calculated this with all the rigor he possessed. He thought, what if the sun were slowly contracting, converting gravitational energy into heat, like a stone that falls and warms up upon hitting the ground? He calculated this could sustain solar luminosity for perhaps 20 or 30 million years. It seemed like a lot, but it wasn't. Geologists of the same era already had evidence that the Earth was much older than that. The rock layers, the fossils, the slow sedimentation of the oceans all pointed to hundreds of millions of years, perhaps more. The sun could not be only 20 million years old if the Earth had evidence of life for much longer periods. There was a problem, a serious one. The sun shone, the Earth was old, and no one knew how to reconcile the two. 19th century physics was standing before a closed door, knocking with its knuckles without anyone on the other side answering. The answer came from a completely unexpected place. It came not from astronomers or geologists, but from the physicists who were taking apart the atom with the tools of the 20th century. Einstein, still a young patent office clerk in Bern, published in a single extraordinary year a series of papers that changed how humanity understood reality. One of these papers, the shortest, the most modest-looking, contained an equation that in its simplest form said the following: mass and energy are the same thing, just with different appearances. Mass is condensed energy. Energy is released mass, and the constant that converts one into the other is the square of the speed of light, a number so immense that even a minuscule amount of mass contains an amount of energy that defies human imagination. Imagine you hold in your hands a single gram of any substance: a gram of sugar, a gram of sand, a gram of water. That gram of matter, if converted entirely into energy, would produce the equivalent of an explosion of thousands of tons of dynamite. Matter is energy trapped in an extremely compact form, and it was this intuition that opened the door 19th century physics could not open. But Einstein's equation alone did not explain how the sun performed this conversion. It said the conversion was possible. It did not say how. And this is where the story became even more interesting, even more human, even more full of that kind of silent effort that rarely appears in school books but constitutes the true texture of science. In the 1920s, physicists began to understand that the atomic nucleus was not indivisible. It was a complex structure made of particles we call protons and neutrons, held together by a force they hadn't even named yet. Francis Aston, a meticulous British physicist passionate about precision, built a device called a mass spectrograph that could measure the weight of atoms with unprecedented accuracy. And he discovered something unsettling. 4 hydrogen atoms, measured individually, weighed more than 1 helium atom. Not much more, but definitely more. The difference was small but real, and Aston knew exactly what it meant. When 4 hydrogen atoms combine to form a helium atom, some mass disappears. And if Einstein's equation was right, that disappearing mass doesn't just vanish, it converts into energy. Arthur Eddington, a British astronomer already famous for experimentally verifying Einstein's general theory of relativity during a solar eclipse, read Aston's results and immediately understood the implication. He wrote, with the clarity only great science communicators possess, that the sun was burning hydrogen, not in the chemical way we burn coal, but in a much deeper way, converting the very substance of hydrogen into helium and releasing the mass difference as pure energy, and that the amount of hydrogen available in the sun was enough to sustain this process for billions of years. It was the answer. But there was a new problem, and it was a problem that seemed insurmountable. For two hydrogen atoms, or more precisely, two protons forming the hydrogen nucleus, to fuse and form helium, they need to get close enough for a force called the strong nuclear force to act between them. This force is extraordinarily powerful, but it has a tiny range. It only acts at distances smaller than the diameter of an atomic nucleus. To get that close, the two protons must overcome the electrical repulsion between them, because both have a positive charge and like charges repel. This electrical barrier is called the Coulomb barrier, named after the French physicist Charles-Augustin de Coulomb, who described the law of electrical repulsion in the late 18th century. In the years following Eddington's intuition, physicists calculated the temperature required for protons to move fast enough to overcome this barrier, and they arrived at a frightening number. The required temperature was much higher than the estimated temperature at the center of the sun. It seemed the sun could not do what Eddington proposed. The barrier was too high, the particles too fast, but still not fast enough. And then one of the strangest and most beautiful aspects of quantum physics entered the scene. A young Russian physicist named George Gamow, who had an explosive personality and an even faster mind, was working in Göttingen, Germany, when he developed, in 1928, a mathematical theory describing a phenomenon with no precedent in classical physics. He showed that subatomic particles do not necessarily need enough energy to climb an energy barrier. They can simply pass through it, as if the barrier did not completely exist. This phenomenon is called quantum tunneling, and it is one of the aspects of reality that most defies intuition. In the world we perceive with our senses, if a ball rolls toward a hill and doesn't have enough energy to reach the top, it stops, rolls back, and never passes to the other side. But in the world of subatomic particles, the rules are different. A particle can have a small but real probability of appearing on the other side of a barrier it classically could not cross. It doesn't go over. It doesn't find an alternative path. It simply appears on the other side. Gamow applied this idea to radioactivity, but Robert Atkinson and Fritz Houtermans quickly realized the same mathematics applied to the problem of stars. The protons at the center of the sun didn't need enough temperature to climb the Coulomb barrier completely. They only needed enough temperature to get close enough for quantum tunneling to do the rest, and the temperatures at the center of the sun, while not as high as classical calculations demanded, were sufficient so that, out of all the billions and billions of collisions happening every second, a tiny fraction resulted in successful fusion. A tiny fraction of an immensely large number is still an immense number, and so the sun burns. Not like a bonfire consuming everything rapidly, but like a contained, slow flame. Regulated by its own internal balance, every second at the center of the sun, hundreds of millions of tons of hydrogen convert into helium. and the mass difference between those hydrogen atoms and the resulting helium, about 0.7% of the original mass, transforms into pure energy. This energy travels through the solar interior, gradually spreading through the successive layers of the star until it emerges at the surface as the light that warms your face. But there is something else happening here, something rarely mentioned when explaining the energy of stars. Fusion at the center of the Sun is not a simple process of 4 protons just joining together at once. It is a chain of steps, a dance of successive reactions that takes a surprising amount of time to complete. An individual proton at the center of the Sun can wait on average billions of years before finding the right conditions to participate in the first step of the fusion chain. The center of the Sun is a place of immense heat and pressure, but fusion itself is a process of almost inconceivable patience on an individual scale. It is statistics that saves everything. There are so many protons, the numbers are so vast, that even with each proton waiting billions of years on average, the total fusion rate is enormous. And this is where the deepest fundamental law comes into play with all its strangeness. Fusion releases energy not just because mass converts to energy as Einstein predicted, but because the strong nuclear force holding the helium together releases an amount of energy upon forming that is greater than the energy required to bring the protons close enough to allow fusion. The resulting helium nucleus is in a lower energy state than the separate protons that constituted it. It is, to some extent, in a valley, a place of deeper energetic rest, and the difference between the energy level of the ingredients and the energy level of the final product is what emerges as radiant energy, as heat, as light. This idea that particles seek lower energy states is one of the most universal in all of physics. It is the same reason water flows downhill, why a sodium atom and a chlorine atom combine to form salt, why a fruit falls from a tree. Nature, at all its levels, tends toward lower energy states, and stars exploit this tendency on a nuclear scale, extracting energy from the differences in stability between different configurations of protons and neutrons. There is a curve that nuclear physicists know very well, and which is perhaps the most important graph for understanding why stars exist and what they produce. It shows the binding energy per nuclear particle for all elements, from the simplest hydrogen to the heaviest elements in existence, and the shape of this curve has something narrative, something almost dramatic about it. It rises rapidly from hydrogen, passes through helium, which is already more stable, continues rising through lithium, beryllium, boron, carbon, nitrogen, oxygen, reaching its maximum peak around iron and nickel, and then it gradually descends through the heavier elements, gold, lead, uranium, down to the artificial elements laboratories create for fractions of a second. This curve says something fundamental. Fusing lighter elements into heavier ones releases energy as long as we are going up the curve, up to iron. From iron onward, fusion no longer releases energy, it consumes it, and fission, the breaking of heavy elements into lighter ones, releases energy when we are going down the curve, starting from very heavy elements toward iron. Iron is the valley of the curve. It is the point of lowest energy per nuclear particle. It is where nuclear matter wants to be. And this fact, so simple to state, so profound in its consequences, is what determines the fate of all stars and explains why the universe has the chemical composition it has. Hans Bethe, a German physicist who emigrated to the United States escaping Nazism and went on to work at Cornell University, dedicated himself in the late 1930s to discovering exactly what the reaction chains were that transformed hydrogen into helium inside stars. He discovered two main chains. The first, which dominates in stars like the Sun, is called the proton-proton chain. It begins with two protons fusing to form a deuterium nucleus, a proton and a neutron together, releasing a particle called a positron and a neutrino. The deuterium captures another proton and becomes helium-3. Two protons and one neutron. Two helium-3 nuclei meet and form helium-4, two protons and two neutrons, releasing the two extra protons back into the plasma, available to restart the chain. It is a cycle that closes upon itself, using its own products as catalysts for the next steps. The elegance of this reaction chain is of an almost musical beauty. It has a beginning, a middle, and a kind of resolution that immediately turns into a beginning again. The second chain, which dominates in stars more massive and hotter than the Sun, uses carbon, nitrogen, and oxygen as catalysts to convert hydrogen into helium. This chain was discovered almost simultaneously by Bethe and the German physicist Carl Friedrich von Weizsäcker, and is called the CNO cycle after the initials of the three elements involved. Carbon acts as a sort of scaffold, capturing protons, transforming into other elements, releasing helium at the end of the cycle, and returning to being carbon to start over. Carbon is not consumed in this chain. It is a facilitator, a catalyst, an element that lends its presence so others can transform, exiting at the end exactly as it entered. And this raises a question that will resonate in silence as your breathing slows. If carbon is necessary for the CNO cycle in massive stars, but the primordial universe had no carbon, where was the carbon that allowed the first massive stars to function this way? The answer implies an order of stellar generations, a sequence of creation and destruction and recreation that is more intricate than it seems at first glance, and which inevitably leads us to the question of how carbon was created in the first place. But before getting there is the fundamental imbalance we mentioned, this tension between two forces that never rests. Gravity wants to contract the star. The star's core, expanded by the immense heat of fusion, resists this contraction. Every photon of energy that fusion produces creates pressure. Every unit of heat pushes outward. And gravity, relentless and without memory, pushes inward. Imagine you are holding a balloon from the inside with all your strength, while someone on the outside compresses it equally. Neither yields. The balloon remains the same size not because the forces are non-existent, but because they cancel each other out perfectly. This is the balance physicists call hydrostatic equilibrium, and it is the life condition of a star. As long as fusion produces enough energy to generate enough pressure to counteract gravity, the star remains stable, the same size, the same brightness, the same character. But fusion consumes fuel. Slowly, patiently, but inevitably. The hydrogen in the core is gradually converted into helium, and the newly created helium does not fuse under the same temperature and pressure conditions that hydrogen did. Helium needs much higher temperatures for the repulsion between its nuclei to be overcome. So the helium accumulates in the center like ash, and the ash does not burn on its own. What happens when the ash accumulates? When the helium core grows while the still active hydrogen shell moves outward? When gravity begins to feel the resistance at the center weakening, is one of the most dramatic stories in physics. And understanding this local process, this small scale of transformation in a single core of a single star, with its fragile balance and silent accumulation of nuclear ash, is the key to understanding what happens when this process repeats on a scale of billions of years, in successive layers of increasingly heavier elements, in sequences of collapse and reheating that dig deeper and deeper into the nuclear energy curve until something decisive finally gives way. When the helium core grows large enough, gravity wins. Not all at once, not in an immediate catastrophic way, but gradually and inexorably, like a musical phrase changing key while you are still listening to the previous note. The center of the star begins to contract because hydrogen fusion there has ceased, and there is no longer enough pressure to maintain equilibrium. But this collapse is neither silent nor inert. The contraction releases gravitational energy, and this energy has to go somewhere. Part of it heats the core itself. Part of it migrates outward and heats the outer layers with a new intensity, different from what the star knew during its long, stable life on the main sequence. What emerges from this local process is a pattern that repeats with astonishing regularity in stars of similar masses throughout the galaxy. It is not a coincidence. It is the geometry of nuclear physics and gravitation working together. And when these two forces interact under the same initial conditions, they produce the same results. The star you observe 12,000 light-years away, and the star your telescope barely resolves in a neighboring galaxy, are, at this moment, possibly undergoing the same structural transition our Sun will one day undergo. This is the power of a physical law. It knows no geographical or historical borders. It works here and there, now and 10 billion years ago, and will work 10 billion years from now. The pattern that emerges when the helium core begins to contract is called a layered structure, and it is one of the most elegant ways nature has found to organize reactions in a temporal sequence. Imagine an inert helium core contracting and heating up. Around this core, a very thin shell where hydrogen still fuses with renewed fury, now fueled by the extra heat from the contraction. Further out, layers of cooler hydrogen, and beyond them, the stellar envelope expanding under this new pressure. The star grows outward at the same time it plunges inward. It becomes a red giant. This transition from main sequence star to red giant is one of the deepest structural changes a moderate mass star can experience. The radius increases by a factor that can exceed 100. The surface cools because the same luminosity is now distributed over a much larger area. The star's color changes from yellow-white to orange, and then to red. Internally, however, the opposite of the surface coolness is happening. The core is becoming hotter and hotter, denser and denser, increasingly pressed by the mass accumulating above it. There is a precise limit to how much the helium core can grow before something changes. This limit is not arbitrary. It is determined by the competition between the weight of the layers above and the resistance the degenerate material offers. In low and intermediate mass stars, the electrons in the helium core eventually become degenerate, meaning the pressure they exert no longer depends on temperature, but only on density. This creates an unprecedented situation in stellar physics. You have a core that can absorb heat without expanding, without cooling, without regulating the reaction that will eventually happen in it. It is a core with no thermostat. When the temperature in the helium core finally reaches the value needed for 2 helium nuclei to start fusing, the reaction begins. But because the core is degenerate, the energy released by fusion does not make the core expand. It simply gets hotter, and the hotter it gets, the faster the fusion occurs. And the faster it occurs, the hotter it gets. In minutes, what could have been a smooth process becomes a flash, a contained nuclear explosion inside the star's core that can release in a few minutes more energy than the sun radiates in millions of years. Not an explosion that destroys the star, but one that completely reorganizes it. This event is called the helium flash, and for a long time astronomers knew it had to exist before fully understanding why. Stars in globular clusters, which are like natural laboratories for studying stellar populations of the same age and composition, showed a peculiar pattern. There was an abrupt disappearance of stars at the top of the giant branch, and a sudden reappearance of them in a different position on the Hertzsprung-Russell diagram, the fundamental graph that organizes stars by luminosity and temperature. For decades, this gap seemed like a mysterious lacuna. Later, it was realized that stars pass through the helium flash so quickly that there simply aren't enough of them in this phase to be observed in a finite population. The rapidity of the event is the very reason it seems absent. Einar Hertzsprung and Henry Norris Russell, who independently developed this diagram in the early 20th century, had no way of knowing how powerful it would become as a tool for understanding stellar evolution. What they did was observe that stars do not distribute randomly when you plot their luminosity against their temperature or color. They group into sequences, into branches, into bands, and each grouping corresponds to a specific internal physical state. The diagram bearing their names is, in a sense, a map of possible equilibrium states for a star, and stars only exist where physics allows them to. After the helium flash, the core's degeneracy is lifted. The core can now expand, can regulate its temperature, and helium fusion settles into a calmer, more sustainable pace. 3 helium nuclei, in a 2-step process called the triple alpha process, combine to form a carbon nucleus. This process is remarkable for reasons that go beyond nuclear chemistry. It requires a coincidence that, when discovered, deeply surprised physics. Fred Hoyle, in the 1950s, was working on the problem of how carbon could be produced in sufficient abundance inside stars to explain the abundance we observe in the universe. Carbon is the fundamental element of organic chemistry, of life, of practically everything biochemically interesting. If stars didn't produce it efficiently, the universe would be essentially sterile. Hoyle calculated that for the triple alpha process to work efficiently, the carbon nucleus would need to have a resonant energy level at a specific value, a value that had not yet been measured in the laboratory. He made the prediction before the experiment. When Willie Fowler and his team at Caltech measured the energy spectrum of carbon, they found exactly what Hoyle had predicted. The resonance existed. Carbon can be made inside stars because it has an excited state whose energy level almost perfectly matches the combined energy of 3 helium nuclei at a typical giant core temperature. If this level were just a small percentage different, the process would be too inefficient. Carbon would be rare in the cosmos. Life as we know it would be impossible. Hoyle was disturbed by this coincidence for the rest of his life. He even suggested it implied some form of fine-tuning of the universe, some deeper structure ensuring physics was compatible with the existence of complex beings. This idea entered the philosophy of science under the name of the anthropic principle, which has many formulations and generates much controversy. What is undeniable, however, is the observational fact. The constants of physics are such that carbon can be produced in quantity inside stars, and this is not trivial. Once helium fusion is established in the core, the star enters a relatively stable period, which, although much shorter than its main sequence phase, has its own internal logic. The produced carbon accumulates. Oxygen is also produced, because a carbon nucleus can capture another helium nucleus to form oxygen. The competition between these two reactions, the formation of carbon and its conversion into oxygen, determines the final ratio of carbon to oxygen in the core. And this ratio is a consequence, among other things, of a property of oxygen that is the inverse of what we observe for carbon. The resonant energy level of oxygen that would correspond to this reaction exists, but it is slightly out of tune. This makes the reaction less efficient, meaning the star ends up with a mixture of carbon and oxygen instead of all the carbon being converted. This ratio between carbon and oxygen has consequences that propagate to future generations of stars. The material the star eventually expels into interstellar space carries this signature. The gas clouds from which subsequent stars form inherit this composition. The chemistry that happens in those clouds, the molecules that form, the conditions preceding the formation of new stellar and planetary systems, all depend in part on this ratio established in the cores of previous stars. A star's past is embedded in the natal environment of all subsequent stars. For stars with sufficiently large mass, the process does not stop at helium. After the helium in the core is exhausted, an inert carbon-oxygen core forms and begins to contract. The resulting heating eventually allows a carbon fusion, which in turn produces neon, magnesium, and a series of other elements. Then neon fuses, oxygen fuses, and each stage produces a denser, hotter, heavier core. Each stage is also shorter than the previous one, because heavier fuels release less energy per unit mass, and the star, now enormously luminous, needs more energy to sustain itself. The structure that emerges from this successive process is geometric in a way no architect could plan more efficiently. The massive star at the end of its evolution looks like an onion. At the center, an iron core or elements close to iron. Around it, a layer where silicon fuses. Further out, where it is cooler, an oxygen layer. Then carbon, then helium, then hydrogen. Each layer represents the last stage of fusion that region can sustain under local temperature and pressure conditions. Each layer is, at the same time, the product of the previous layer and the fuel feeding the inner layer. This layered structure was inferred long before it could be directly observed. Direct observation of a star's interior is still impossible for light. Stars are opaque, but they are not opaque to neutrinos, which are particles that interact so weakly with matter they pass through any amount of stellar material practically unimpeded. And they are not opaque to pressure waves propagating through the interior, which reach the surface as subtle oscillations in brightness or the velocity of the outer layers. Asteroseismology, the study of these oscillations, allows astronomers to do something analogous to what geologists do when studying the Earth's interior from seismic waves. The surface vibrates in ways that carry information about what lies below. From these vibrations, it was possible to confirm aspects of the solar internal structure that theoretical models predicted: the depth of the sun's convective zone, the composition gradient between fusing and non-fusing regions, the variation of the speed of sound with depth. All these details could be extracted from the solar surface's oscillation modes, And this type of confirmation was fundamental, not just for solar physics but for stellar physics in general, because the Sun is the only place where we have data of sufficient resolution to test models in detail. Roger Ulrich, John Liebacher, and Robert Stein, who contributed to establishing asteroseismology in the 1970s, recognized in the solar surface oscillations what was essentially a sonic tomography of an object 150 million kilometers away. The idea that one could listen to the interior of a star, in the sense of using waves to map internal structures, completely transformed what was possible to know about conditions in stellar cores. The geometry of the internal layers of a massive star is also influenced by something that seems at first glance irrelevant to nuclear fusion: rotation. A rotating star is not spherical. It is flattened at the poles and bulging at the equator, and this flattening modifies internal pressure and temperature gradients in ways that affect where and how convection occurs, where fusion layers meet and mix, and how much of the products of a fusion phase are transported upward and mixed with cooler outer layers before the star dies. Stars that spin rapidly have more mixed internal lives. Fusion products travel further through the interior. The core is exposed to the envelope, and the envelope is contaminated by the core in ways slow stars do not experience. This has observable consequences. Massive stars that spin rapidly show on their surface elements that would normally only be found in the innermost layers. Nitrogen, for example, is produced in a series of reactions that normally occur below the surface, but rapidly rotating stars frequently show nitrogen enrichment on the surface because rotational mixing transported that nitrogen upward. This spectroscopic signature has been used to identify rapidly rotating stars and to calibrate rotational mixing models in stellar evolution codes. Rotation also affects the star's final fate. A rapidly rotating, massive star, when it eventually collapses, can produce a central object that spins very rapidly. This rotation can channel the jet of material and energy emerging from the collapse in ways very different from a slower collapse. The most energetic explosions, the so-called hypernovae, and the events that produce long-duration gamma-ray bursts seem to be associated with rapidly rotating progenitor stars. The speed the star accumulated during its formation and life is preserved until the final moment, and influences how it dies and what it leaves behind. But the layered structure, the emergent order physics produces without any component planning it, goes beyond the internal geometry of an individual star. When looking at the galaxy as a whole, when mapping where stars of different types and evolutionary stages are, another level of organization emerges. Stars do not distribute evenly across the galactic disk. They concentrate in spirals, and in regions of highest concentration, especially in the spiral arms, the density of interstellar gas is higher, the star formation rate is higher, and therefore the rate of heavy element production is higher. The spiral arms of the galaxy are, in this sense, element factories. They are not solid physical structures, like spokes of a wheel. They are density waves traveling through the galactic disk, compressing the gas they encounter, stimulating the formation of new stars, concentrating stellar processing. And since the most massive stars live briefly, they tend to die near where they were born, which is near the spiral arms. The supernova explosions that disperse the produced elements concentrate, therefore, in these star-forming regions. This creates chemical composition gradients along the galactic disk. The innermost regions of the galaxy, where stellar density and star formation activity have historically been greater, are more enriched in heavy elements than the outer regions. Stars formed near the galactic center tend to have higher metallicity, which is the term astronomers use to indicate the abundance of all elements heavier than helium, regardless of whether they are metals in the chemical sense. Stars in the galactic periphery tend to have lower metallicity. This metallicity gradient is not just an aesthetic curiosity. It has consequences for planet formation. Planetary systems of stars with higher metallicity tend to have a higher probability of containing rocky planets with compositions rich in iron, silicon, and carbon. Our own solar system, born in a region of intermediate metallicity about 4.6 billion years ago, bears the signature of all this prior galactic history. The composition of the Earth, the other planets, the comets and asteroids traversing the solar system all reflect the composition of the interstellar gas clouds from which the Sun formed. And this composition in turn reflects the contributions of countless previous generations of stars. The patterns that emerge on a large scale, therefore, are the sum of all local processes that occurred in each individual star throughout galactic history. Every star that lived and died, every core that collapsed, every envelope that was expelled, contributed a measurable amount of elements to the interstellar medium. And the interstellar medium, mixed and reprocessed over billions of years, eventually condensed into new stars that in turn contributed more. It is a cycle of cumulative enrichment. The astrophysicist William Fowler, who worked with Hoyle and years later received the Nobel Prize for his work on stellar nucleosynthesis, used to say that understanding how elements are formed inside stars was understanding the origin of the matter we know. The fundamental paper he published jointly with Hoyle, Margaret Burbidge, and Geoffrey Burbidge in 1957, known by the acronym B2FH, but which we will describe here as the work of the Four, established the foundations of the entire field. In it, the authors identified the main processes of stellar nucleosynthesis and showed how each family of elements corresponds to a specific physical process occurring under specific conditions inside stars. What they built was a coherent narrative linking the periodic table to hot plasma physics, gravitation, and stellar explosions. Each element was no longer just a chemical symbol on a chart. It was the product of a physical process that occurred at some point, in some star, under specific conditions. The carbon in the pencil you use to write was forged by the triple alpha process inside a red giant that existed before our Sun. The iron in your blood was created in the innermost layers of a massive star in the instants preceding its death. The oxygen you breathe was produced in multiple fusion phases in multiple types of stars over billions of years. The organization that emerges from all these local processes into global galactic and chemical patterns would already be impressive if it depended only on the mechanisms we have described so far. The sequential thermonuclear fusions, the layered structure, the collapses and reheatings, the dispersion into the interstellar medium, and recondensation into new generations of stars. But there is an additional ingredient that amplifies everything, that accelerates and diversifies and extremizes the results, that takes the ordered patterns regular fusion produces and subjects them to conditions so extreme that new territories of the periodic table open up suddenly. Without this ingredient, the galaxy would be a chemically simpler, more predictable place, with less of the elemental diversity that makes the material complexity we observe possible. With it, the story becomes much richer. That ingredient is the supernova. Not the supernova as a distant spectacle, as a colorful photograph in an observatory catalog, as a scientific abstraction existing only in equations and telescopes. The supernova as a real event, as a physical process of such organized violence it seems almost intentional, as a mechanism the galaxy developed over billions of years to do what regular fusion, by itself, could never completely achieve. The supernova is the amplifier. Not in the metaphorical sense of something making things bigger or more intense in a vague way, but in the technical and precise sense of a mechanism that takes already extreme conditions and elevates them by factors that defy everyday intuition. To understand why the supernova is an amplifier and not just a destroyer, one must understand what happens in the fractions of a second when the core of a massive star collapses. The star spent decades or millions of years building layers of progressively heavier elements, fusing hydrogen into helium, helium into carbon, carbon into oxygen and neon and magnesium, eventually reaching silicon and sulfur and calcium, accumulating at the center a growing mass of iron and nickel that simply does not participate in any fusion reaction that releases energy. And then, in a moment that can be measured in tenths of a second, the iron core reaches a critical mass. The electron degeneracy pressure can no longer support the weight of the layers above, and everything collapses inward. The core, which was roughly the size of a planet like Earth, compresses in less than a second into a sphere with a diameter comparable to a medium-sized city. This process releases an amount of energy that is difficult to express without words losing meaning. The gravitational energy released in this collapse is on the order of 3 × 10⁻⁶ joules, which is about 100 times more energy than our Sun will release in its entire 10 billion-year lifespan. And this entire amount is released in a matter of seconds. 98% of this energy leaves in the form of neutrinos, uncharged particles with negligible mass that interact so weakly with matter they can traverse a star's interior almost unimpeded. Neutrinos are the invisible mechanism behind everything. When the core collapses, it temporarily becomes so dense that even neutrinos cannot escape immediately. The newly formed core, called a proto-neutron star, traps the neutrinos for a fraction of a second, and when they finally break out, they carry with them enough energy to disintegrate the entire star. The shock wave born in this collapse travels outward through the star's outer layers, and when the neutrinos interact with this shock wave, they transfer enough energy so the explosion not only continues, but gains strength, hurling the outer layers into space at speeds that can reach 10% the speed of light. What just happened is not just destruction. It is a process that creates conditions that do not exist anywhere else in the known universe. When the shock wave passes through the star's outer layers, it creates temperatures and pressures that far exceed what regular fusion produces in the stellar interior during millions of years of stable life. The process called explosive nucleosynthesis occurs in these layers in fractions of a second, producing elements that could not have been created in any other way inside a star in equilibrium. The silicon, which was being slowly fused in the core for weeks before the collapse, is suddenly bombarded by a temperature wave so high that reactions that would normally take years occur in milliseconds. The process of explosive silicon burning deserves special attention because it is one of the most productive in terms of elemental diversity. When the shock wave heats the silicon layer to temperatures above 5 billion kelvins, silicon and sulfur and calcium and titanium and chromium and vanadium participate in a series of chain reactions that produce in a few seconds what would take decades of quiet fusion to create. The iron group elements, those with atomic numbers close to iron, are synthesized in abundances that would not be achieved otherwise. Cobalt, manganese, scandium, substantial parts of the nickel existing in the universe, all have in explosive nucleosynthesis one of their most important sources. But the amplifier does not stop at iron and its neighbors. The supernova opens territories of the periodic table that are completely inaccessible to regular fusion because they require you to add neutrons to existing nuclei with a speed that the process called the S process, the one that happens slowly in asymptotic giant branch stars, simply cannot achieve. The S process, which stands for slow process, operates by adding one neutron at a time to a nucleus and waiting for the nucleus to undergo beta decay before adding the next. This method is precise and methodical, and produces elements up to bismuth and lead, but it has a fundamental limit. It cannot create elements in regions of the periodic table where intermediate nuclei are too unstable to wait for decay. The supernova releases this limit. The R process, where the R stands for rapid, occurs when a neutron density so extraordinary is available that nuclei absorb dozens or hundreds of neutrons almost simultaneously, before any decay can occur. This pushes nuclei far beyond what would be stable under normal conditions, creating extremely neutron-rich nuclei that decay in a cascade when conditions normalize, producing heavy elements that simply would not exist otherwise. Gold, silver, platinum, uranium, thorium, lead of certain origins, iridium, osmium, large fractions of all elements heavier than iron, these are the children of the R process. For many years, it was believed that supernovae were the only environment where the R process could occur, and they certainly contribute to it. But more recent discoveries revealed there is another environment where the R process occurs with even greater intensity. In September 2017, when two gravitational wave telescopes detected the signal called GW1 Sensenno 817, and observatories across the planet simultaneously observed the glow that appeared in the galaxy NGC 4993, it became clear that the merger of two neutron stars is probably the main producer of heavy elements through the R process. This event, called a kilonova, produced in a few hours an amount of gold estimated between 10 and 100 Earth masses, along with comparable proportions of other heavy elements. The kilonova is the supreme amplifier. It combines two objects that are already the result of previous amplifications, two stars that lived and died as supernovae, and makes them collide in an explosion that concentrates all the matter of two neutron stars, each with a mass comparable to the Sun, but condensed into a sphere about 20 kilometers in diameter, into a single merger event lasting fractions of a second. The neutron density available in this event exceeds anything a conventional supernova can produce, and the R process occurs with an efficiency that makes every kilonova an unparalleled heavy element factory. The gold you wear, if you wear a piece of jewelry, if there is a ring or a necklace or an earring somewhere near you, that gold has a story that begins in two dense, dead objects, orbiting each other for millions of years, losing energy in the form of gravitational waves, slowly spiraling toward one another, until the separation between them falls below a critical threshold, and they merge in a fraction of a second of concentrated energy that has no parallel in the everyday cosmos. The neutrons released in this merger bombarded existing nuclei and created the gold that was later dispersed through space, incorporated into gas and dust clouds, condensed into solar systems, accumulated in planets, extracted from the Earth by beings who developed the capacity to recognize its shine and attribute value to it. The visible manifestations of all these processes are some of the most spectacular human telescopes have ever recorded. A supernova, at its peak, brightness can outshine the entire galaxy hosting it, becoming visible from distances that take light tens of millions of years to cross. Supernova SN 1987A, which occurred in the Large Magellanic Cloud about 168,000 light-years away, was visible to the naked eye for weeks and provided data that confirmed theoretical predictions about element production and neutrino emission with a precision that transformed astrophysics. The classification of supernovae by type carries within it a story of discovery that reflects the complexity of the mechanisms behind each event. Type 2 supernovae are those that produce hydrogen lines in their spectra, indicating the star had not lost its outer layers before exploding. They are the result of massive stars, usually with more than 8 solar masses, that kept their hydrogen envelopes until the moment of collapse. The name Type 2 was not chosen for any intrinsic logic, but from a historical sequence of discoveries and spectroscopic classifications that was refined over decades. Type 1 supernovae, which lack hydrogen lines, were subdivided into subcategories reflecting fundamentally different mechanisms. Those of subtype 1a are of extraordinary cosmological importance because they are believed to all explode with approximately the same intrinsic luminosity, making them standard candles astronomers use to measure distances in the universe. They result from white dwarfs in binary systems accumulating matter from a companion star until reaching a critical limit near 1.4 solar masses, called the Chandrasekhar limit, in honor of the Indian astrophysicist Subramanian Chandrasekhar, who calculated this value when he was just 22 years old aboard a ship between India and England. When the white dwarf reaches this mass, the explosive fusion of the carbon and oxygen comprising its interior begins uncontrollably, and the star destroys itself completely, leaving no remnant. Subtype 1b and 1c supernovae are massive stars that lost their hydrogen envelopes, and in the case of subtype 1c, also the helium before exploding. They result from very massive stars that had intense stellar winds or mass transfer to binary companions. What matters is not just the classification itself, but what it reveals about the diversity of paths leading to the same final explosion, and about how each different path produces slightly different nucleosynthesis patterns. Supernova remnants are the most enduring manifestations of these events. When the explosion occurs and materials are hurled into space, they form expanding structures of ionized gas and dust that remain visible for tens of thousands of years. The Crab Nebula in the constellation Taurus is the result of a supernova observed by Chinese and Islamic astronomers in the year 1054 of our era. What they saw as a bright new star in the daytime sky is today an expanding cloud of filaments 11 light-years in diameter, still expanding at about 1,500 kilometers per second. At the center of this cloud pulses a neutron star spinning 30 times a second, emitting regular pulses of radiation that reach Earth with a precision rivaling the best atomic clocks. What you would perceive if you could observe a supernova remnant with eyes adapted to other frequencies would be something the visible spectrum does not fully capture. In radio, it shines with a specific intensity resulting from electrons spiraling along magnetic field lines at relativistic speeds. In X-rays, it radiates with a temperature of tens of millions of kelvins. the residual heat of the shock wave continuing to heat the interstellar medium as it expands. In infrared, it reveals newly formed dust, silicate, and carbon grains that condensed from the expanded gas, and that one day could be the grains around which planets will form. Interstellar dust is the most intimate and least obvious manifestation of all these processes. It is everywhere, between the stars, in molecular clouds, in the matter composing disks around young stars. You cannot see it directly, but it manifests indirectly in ways astronomers have learned to interpret. It reddens the light of distant stars, absorbing blue wavelengths more efficiently than red ones. It creates the dark bands crossing the Milky Way when you observe it from a region without light pollution. It absorbs ultraviolet light from young stars and re-emits it in the infrared, making star-forming regions glow intensely at wavelengths the human eye cannot detect. These dust grains, each with typical dimensions of a few hundred nanometers, a fraction of the wavelength of visible light, are composed of materials stars produced and dispersed. Silicate grains, made of silicon and oxygen and magnesium and iron compounds, condensed in the cooled atmospheres of red giants or in supernova ejecta. Carbon grains, including graphite and more complex forms, came from carbon-rich stars that expelled their outer layers. Some of these grains are so old they predate the solar system itself, having condensed in stars that lived and died before the sun formed, and we can identify them in meteorites because they carry isotopic signatures that do not match the material of our solar system. Meteorites are the most concrete archive we have of this entire process. Certain primitive meteorites, called carbonaceous chondrites, preserved pre-solar grains that survived the formation of the solar system without being completely processed. When you analyze these grains individually, you find isotopic ratios that unequivocally point to specific stellar origins. Silicon carbide grains with carbon ratios that could only have been produced in asymptotic giant branch stars. Aluminum oxide grains with signatures of certain oxygen isotopes, indicating they condensed in red giants of a particular chemical composition. Nanometric diamonds carrying xenon with an isotopic composition indicating a supernova origin. Touching a primitive meteorite, if you ever have that opportunity, is touching material that was in other stars before our sun existed. The atoms composing that stone, or at least some of them, completed the cycle of stellar condensation, stellar life, supernova dispersion, interstellar travel, incorporation into a molecular cloud, participation in the formation of the solar system, and arrival in the present in a solid object you can hold. The story these atoms carry is measured in billions of years, and in distances no human journey has yet begun to cover. The next time you look at the night sky, if you are in a place dark enough to see the Milky Way, look for the darkest regions, the bands where the starlight seems interrupted. These darknesses are not absences of stars. They are dust clouds blocking the light of stars behind them. Each of these clouds is an archive of past events and a cradle of future events. Inside them, the atom stars created and dispersed are aggregating again, cooling, condensing, following paths that can lead to the formation of new stars and new planetary systems on timescales of a few million years. Inside your own body at this moment, there are atoms that passed through supernovae. It is not a poetic metaphor. It is a statement with concrete empirical support. The calcium in your teeth and bones, the iron in the hemoglobin circulating in your blood, the iodine in your thyroid, the selenium and molybdenum and copper participating in enzymatic reactions, all have stories passing through at least one, and probably many, stellar explosions. The zinc your neurons use to signal across synapses, the magnesium anchoring chlorophyll in the plants you eat, the manganese in your mitochondria, all were forged in stellar furnaces and dispersed by explosions before finding a way, over billions of years, into the interior of a being who now thinks about where they came from. This perception can arrive in different ways. For some, it arrives with a quality of vertigo, the sensation that the boundaries between what is you and what is the universe are less solid than they seemed. For others, it arrives with a sense of belonging, not to a place or a human community, but to a larger process, to a continuity of matter and energy transforming without ever being created or destroyed. For others still, it arrives simply as fascinating information that alters nothing in practical experience, but illuminates the backdrop against which everything happens. Whatever form it takes, there is something curious in the fact that you can perceive this. You can have this perception because you have a brain that evolved the capacity for language and abstraction and causal reasoning. This brain is made of atoms stars created, and the chain going from a supernova to a being thinking about supernova passes through a sequence of steps, each of which depends on very specific conditions, on the abundance of the right elements, on the physical and chemical properties emerging from the nuclear structures stellar fusion produces, on the laws of physics determining how these elements combine to form complex molecules, and eventually biological structures. The system seems, from a certain perspective, to be in a remarkable equilibrium. Stars form, fuse, explode. The interstellar medium receives their products and mixes and cools them. New stars form from the enriched material. The galaxy slowly processes its inventory of primordial hydrogen into heavier elements, generating along the way the chemical complexity that makes worlds like ours possible. Every component of this cycle seems to fit into the others with a precision, giving the impression the system was designed to work this way, that it will continue functioning indefinitely in the same manner. But this impression of balance and stability is misleading. The cycle that seems so robust depends on conditions that are not guaranteed, on processes unfolding on timescales that make their changes invisible in a human life, or even the entire history of civilization, but which are absolutely real from the perspective of billions of years. The hydrogen stars consume does not renew. Every star that ignites, lives, and dies leaves the universe with a little less fuel available for the next generation. Heavy elements accumulate, but the matter that could become new stars is becoming progressively more depleted in the most fundamental element of all. There is an asymmetry at the heart of this seemingly circular cycle. The universe began almost entirely with hydrogen and helium, with traces of lithium and beryllium. And every time a star fuses heavier elements, it is converting a form of stored energy into a form of energy that can no longer be used in the same way to sustain fusion. The iron accumulating in the cores of massive stars is the symbol of this, the end point that cannot advance through fusion without consuming energy instead of releasing it. And although supernovae redistribute and enrich the interstellar medium, they do not restore the consumed hydrogen. The equilibrium, however impressive it seems when observed in individual processes, is resting on a foundation that dissolves very slowly but irreversibly. There is a moment in the most massive stars when calm is no longer possible. It is not a smooth transition like the one leading a young star to find its equilibrium on the main sequence, that state of gentle tension between compressing gravity and expanding radiation pressure. What happens in the entrails of a huge star after decades or centuries of accelerated fusion is different in nature. It is the approach of a threshold the universe did not build with alternative exits. The star has reached iron, or is reaching it, and the physics that sustained its entire existence begins to betray it. To understand why this threshold exists, one must remember that a star's entire stability rests on a simple premise. Nuclear fusion releases energy. This energy generates pressure. This pressure sustains the structure against gravity. When carbon burns into oxygen and magnesium, energy is released. When oxygen burns into silicon and sulfur, energy is released. When silicon burns into iron and nickel, energy is still released, but in progressively smaller amounts per reaction. Iron releases no energy at all when fusing with other iron. On the contrary, to fuse iron into even heavier elements, energy must be supplied to the system. Iron is the lowest point of a nuclear energy landscape, the valley from which no fusion reaction can escape on its own. While this occurs in the core, the outer layers are still burning. Silicon burns in a shell around the iron core, oxygen burns in a more outer shell, carbon in a shell further out, helium in the next shell, hydrogen in the outermost of all. This shell structure is a marvel of thermodynamic organization, a sequence of nested reactions each feeding and regulating the others. But the iron core at the center grows. Every reaction in the silicon shell produces more iron draining inward. Every reaction in every outer shell adds its products to the accumulation. The iron core cannot sustain itself through fusion, so it sustains itself only by electron degeneracy pressure, that quantum resistance preventing two fermions from occupying the same state. There is a limit to this resistance. Chandrasekhar calculated it in terms of stellar mass. When the iron core exceeds approximately 1.4 solar masses, electron degeneracy pressure is no longer able to support the weight of the layers above. This threshold has a name, a value, a cold mathematical elegance contrasting completely with what it triggers. When the iron core of a massive star crosses this limit, collapse begins in less than a second. 1 second is more than enough time to destroy a star that took millions of years to form. The core, which has a mass greater than the entire Sun contained in a volume the size of a planet, begins collapsing under its own gravity with a hallucinatory acceleration. Electrons are forced to combine with the protons of the iron nuclei in a process called electron capture, producing neutrons and emitting neutrinos. These neutrinos escape almost freely at first, carrying an amount of energy exceeding the Sun's total luminosity for billions of years, all emitted in less than 10 seconds. The core loses support. The collapse speed increases to 1/4 the speed of light. The material falls. Then something occurs that no simple equation can fully capture. The core reaches nuclear density. At this density, matter behaves like a single gigantic atomic nucleus, and the strong nuclear force becomes repulsive at short distances. The collapse stops abruptly. The material still falling from the outer layers meets this newly formed core, which is now essentially a nascent neutron star with a stiffness bordering on the incomprehensible, and bounces. A shock wave propagates outward through the layers that were still falling. This shock wave, under normal conditions, should be enough to expel the star's outer layers. But physics is not that simple. As the wave propagates, it passes through the iron-rich layers still falling, and dissipates energy, dissociating the iron nuclei back into protons and neutrons. The shock wave loses strength, slows down, threatens to stall at a radius of a few hundred kilometers. For a moment, it seems the collapse will simply continue, and the entire star will disappear into a black hole without ceremony. But neutrinos save the day. Under normal conditions, neutrinos pass through matter practically without interaction, which is why we can detect them from supernovae at immense distances. But the matter in the region near the newly collapsed core is so dense that even neutrinos need a brief time to escape. In this brief time, a minuscule fraction of the neutrinos deposits energy into the stalled shock wave. The fraction seems small, but the total amount of neutrinos is so extravagant that even 1% absorption represents enough energy to relaunch the explosion. The outer layers are swept outward. The supernova happens. The brilliance reaching observers on Earth's surface or in orbiting telescopes is the reflection of all this violence. A core collapse supernova can emit more light for a few weeks than the entire galaxy containing it. Tens of billions of stars combined, all eclipsed by this single event. What we see in optical wavelengths is just the envelope expanding, the material of the outer layers being swept and heated by the shock, glowing in spectral lines betraying its chemical composition. We see hydrogen, helium, silicon, sulfur, oxygen, each with its characteristic emission and absorption signature. What we do not see directly, but know is there, is the nucleosynthesis process occurring in the moments and hours following the explosion. When the shock wave heats the innermost layers to temperatures above 5 billion degrees, photodissociation and recapture reactions create conditions for forming nuclei that would never exist in equilibrium conditions. The rapid neutron capture process, which physicists call the R process, occurs in this environment of extraordinary neutron density. Nucleus after nucleus captures neutrons faster than it can radioactively decay, creating unstable nuclei existing only for fractions of a second, before emitting electrons and stabilizing as heavy isotopes of elements ranging from zinc to uranium, the gold in the oceans, the platinum in automobile catalysts, the uranium in nuclear plants. All were forged in these moments of collapse and explosion. Humanity has learned to observe these events in ways that would have seemed magical to astronomers of past centuries. Networks of telescopes around the planet automatically monitor millions of galaxies for points of light that did not exist the night before. Image processing algorithms compare galaxy photographs with reference images taken days or weeks earlier, and when a new star appears, an automatic alert is triggered to observatories worldwide. Telescopes reorient in minutes. Spectra are taken. Light curves are monitored hour by hour, recording how the brightness grows and then slowly diminishes over weeks and months. Neutrino detectors complete the picture in ways light never could. When a supernova collapses its core, neutrinos arrive before light by hours, because they escape the collapsed core immediately, while light has to fight through the star's opaque layers before escaping. In 1987, when the closest supernova in centuries exploded in the Large Magellanic Cloud, neutrino detectors in Japan and the United States recorded a burst of 19 neutrinos arriving over 13 seconds. 19 neutrinos, against a practically zero noise background, was enough to confirm the entire core collapse theory. Measure the total energy released, and establish that neutrinos have a very small but non-zero mass. 19 particles written on graphite paper and magnetic tape, witnesses to a cosmic catastrophe 160,000 light-years away. The structures these explosions leave behind are some of the most dynamic and persistent the universe produces. Supernova nebulae expand for thousands of years. Bubbles of heated and shocked gas glowing in X-ray, ultraviolet, and visible light wavelengths. The Crab Nebula, which Chinese astronomers recorded as a new star visible to the naked eye in 1054 of the Common Era, is still expanding, still glowing, still being fueled by the pulsar at its center. This pulsar, the neutron star left by the collapse, spins 30 times a second, emitting radio and X-ray beams with the regularity of a nuclear clock. Each rotation dissipates rotational energy, fueling a particle wind that will inflate the nebula for a long time to come. Pulsars, as objects of study revealed physics the terrestrial laboratory will never be able to reproduce. The neutron star has a mass greater than the Sun, compressed into a volume of less than 20 kilometers in radius. The density in its interior exceeds the density of atomic nuclei by perhaps an order of magnitude. Matter there can exist in states that have no definitive name yet. Quark condensates, neutron superfluids, proton superconductors. The magnetic field on the surface of a typical neutron star is 1 trillion times stronger than Earth's magnetic field. In extreme cases called magnetars, this field is thousands of times more intense still, capable of deforming the atomic orbitals of any approaching atom and emitting X-ray and gamma-ray bursts we can detect at distances of tens of thousands of light-years. Supernova remnants also shape the interstellar medium in ways determining where the next generations of stars will form. A supernova shock wave expands for thousands of light-years, compressing the gas and dust it encounters, sometimes triggering gravitational collapses leading to new stars, other times heating the gas to temperatures so high it becomes stable against collapse for millions of years. Supernovae are simultaneously the most generous creators and the most violent destroyers of conditions for star formation. Each explosion sculpts the cosmic environment around it, creating shells and filaments of gas persisting as visible structures for tens of thousands of years. There are also even more dramatic events occurring when conditions are slightly different. When the collapsing star is sufficiently massive, perhaps above 20 or 25 solar masses, the collapse may not stop at the neutron star phase. The core can continue collapsing until not even nuclear matter pressure is enough to halt gravity, and a black hole forms instead. In these cases, the supernova may be weaker, because the black hole swallows a larger portion of the material before the shock wave can propagate effectively. In extreme cases, the star may simply vanish from sight without a visible explosion, collapsing directly in silence into the singularity. And there are events called hypernovae, or core collapse supernovae with relativistic jets, where the rapid rotation of the collapsed core channels energy into jets traveling at speeds close to light along the star's rotation axis. These jets pierce the star's outer layers and can extend for enormous distances around it, emitting gamma rays in a burst lasting from fractions of a second to minutes and visible billions of light years away. Gamma ray bursts are the most energetic events we know in the universe, releasing in seconds more energy than the Sun emits in 10 billion years. Detectors on satellites like the Fermi Gamma Ray Space Telescope record several of these bursts per day, coming from galaxies so distant the light reaching us left when the universe was only 1 billion years old. Humanity has learned to use these events as measurement tools beyond simple observation. Type 1. A supernovae, occurring when a white dwarf in a binary system accumulates mass from a companion star until exceeding the Chandrasekhar threshold. Explode with such consistent luminosity, they serve as standard candles for measuring cosmic distances. It was precisely the use of these supernovae as distance measurers in the late 1990s that revealed the universe's expansion is accelerating, leading to the concept of dark energy. The carbon, oxygen, and silicon atoms forged inside intermediate mass stars and later distributed in space, when accumulated in a white dwarf and then exploded, became cosmology instruments rewriting our understanding of the universe's structure and fate. While you rest somewhere in the Milky Way, an iron core is growing, silently, gram by gram, second by second, in a star that shone for perhaps 10 million years and is completely unaware of the approaching precipice. Somewhere, a shockwave is still propagating through what was once a star, sweeping into interstellar space layers rich in oxygen, silicon, magnesium, iron, plus the precious traces of gold and uranium forged in the most intense instance of collapse. Somewhere, a pulsar spins and pulses and heats the remnant around it, teaching the physics of matter states we will never reproduce in a laboratory. These events are not rare on a galactic scale. Our Milky Way probably experiences a few supernovae per century, happening somewhere in the disk or spiral arms, most invisible to the naked eye because interstellar dust blocks visible light from the most distant regions. What all this violence produces, however, does not exist in isolation. Every supernova explosion, every propagating shockwave, every expanding and eventually cooling bubble of heated gas, every filament of enriched material floating in the interstellar medium, is part of an exchange system involving structures much larger than the individual star, much larger than the individual remnant, much larger even than the immediate spiral arm of the galaxy. Supernovae do not end where their brightness fades. They reverberate. The waves a supernova sends into the interstellar medium do not simply dissipate because the visible light of the event has gone out. They continue, transformed into increasingly less obvious forms of disturbance, increasingly diffuse, until they become practically indistinguishable from the general fabric of gas and dust filling the spaces between stars. But indistinguishable is not the same as absent. The material this shockwave pushed, compressed, heated, and then left behind still carries the memory of the explosion in its chemical composition, in its temperature, in its spatial distribution, in its residual velocity. And this memory will meet other stars, other molecular clouds, other spiral arms, and will leave a trail of influence there too. The main partner in this exchange system is the galaxy itself considered as an organism, not the galaxy as a collection of stars individually indifferent to one another, but the galaxy as a fluid, circulating structure, with currents of matter rising and falling from the galactic plane, condensing into clouds and dispersing again into diffuse gas, migrating from one spiral arm to another over tens of millions of years. The massive stars exploding as supernovae form preferentially in the spiral arms, where the interstellar medium density is higher, and where galactic density waves compress the gas enough to trigger gravitational collapse. And when these stars explode, part of their mechanical energy goes into this same interstellar medium, compressing it again, potentially triggering the formation of new stars on the periphery of the expanding remnant. It is a cycle with localized positive feedback. The death of stars creates the conditions for the birth of stars. But there is also negative feedback on the larger scale. When many supernovae occur in a compact region, as happens when an OB association, a grouping of very massive stars, exhausts its short life in unison, the cumulative effect of the explosions can be devastating to the molecular cloud that spawned them. The overlapping shock waves, the merging bubbles of heated gas, the stellar winds preceding the explosions. All this can sweep the cold gas from an entire region, dissipating the raw material needed for new stars. Star formation temporarily shuts down in that piece of the galaxy. The destruction of old stars interrupted the manufacturing of new stars. This is negative feedback. The process sows the conditions for its own interruption. These two modes of feedback operate on very different timescales. The local compression triggering star formation on the edge of a supernova remnant can occur in a few 100,000 years, a blink of an eye in galactic time. The dissipation of an entire molecular cloud by a collection of explosions can take a few million years, and the recovery of that region, the slow reaccumulation of cold gas, the condensation of new molecular clouds from the dispersed material, can require tens of millions of years. The system operates simultaneously on all these rhythms, with short-lived processes embedded within medium-lived processes, which in turn are embedded within even slower cycles we can barely observe because our existence is too short to catch more than an instant of them. In the short term, which for cosmos physics means decades and centuries, what we observe of an individual supernova is the expansion and cooling of the remnant. The first decades are dominated by X-ray emission, as the shocked gas reaches temperatures of tens of millions of degrees. Over centuries, the remnant cools and begins emitting more strongly in radio and optical wavelengths. Filaments of condensed material become visible. The expansion speed, which can be thousands of kilometers per second in the initial moments, progressively decreases as the swept shell encounters more interstellar material and has to work harder to move. This deceleration is not gradual and smooth. It can be unstable, with parts of the shell moving faster than others depending on the local density of the medium they encounter, creating irregular and interesting structures. Over millions of years, the remnant dissolves completely into the interstellar medium. But the elements the supernova synthesized and expelled do not dissolve in the same way as the shock wave. They persist as chemical components of the diffuse gas, available to be incorporated into future molecular clouds, to be pulled into forming protoplanetary disks, to end up in planets and, eventually, in organisms. The duration between a supernova explosion and the incorporation of its products into a new planet can be on the order of tens of millions to hundreds of millions of years, depending on local conditions. The iron in Mars's core, the oxygen in Earth's oceans, the silicon in Mercury's rocks, all these atoms traveled this path one or more times before arriving where they are. What makes this system especially fascinating for those contemplating its limits is its sensitivity to initial conditions. The physics of how a molecular cloud collapses to form a star is well understood in general terms, but the specific outcome, the mass of the born star, the presence or absence of binary companions, the exact amount of angular momentum in the collapsing core, depends on minuscule details of the initial density, turbulence, and magnetic field distribution within the cloud. These details, by their nature, are impossible to measure with enough precision to make deterministic predictions. The physics is well determined. The initial conditions are irreducibly uncertain. And since the evolution of a massive star and its final fate are sensitive to these initial parameters, the ability to predict what a specific star will do has fundamental limits that are not just technological limits, but limits of principle. This is not a flaw of science, it is a property of the system. And recognizing this property is in itself an advance of knowledge. Knowing something is unpredictable in detail but understandable in statistical patterns is much more useful than either pretending certainty or declaring total ignorance. The science of supernovae operates exactly in this space. We understand very well the mass distribution of exploding stars, the average supernova rate in galaxies of different types, the typical behavior of remnants at different evolutionary stages, the expected chemical composition of the ejecta as a function of the progenitor star's mass. What we cannot do is point to a star and say precisely when it will explode, or describe in atomic detail what will happen inside its collapsing core. This frontier between the understood and the fundamentally uncertain is one of the richest landscapes science inhabits. It becomes visible in discussions about the star Betelgeuse, a red supergiant about 700 light-years from Earth, which has been studied with increasing intensity because it exhibits brightness variations suggesting intense convective activity on its surface, pulsations in the rhythm of its outer layer, signals some interpret as precursors to an imminent explosion on an astronomical timescale. When Betelgeuse dimmed dramatically in late 2019, an intense discussion began about whether that was the signal of an approaching explosion. The answer the data eventually provided was more prosaic: an ejection of material from its surface that cooled and formed dust, temporarily blocking part of the light. But the discussion itself revealed the contours of the frontier. We know enough to recognize the relevant signals, but not enough to interpret each of them with certainty. What makes all this contemplable, in the deepest sense, is the combination of two qualities that rarely appear together. The system is comprehensible and surprising at the same time. Comprehensible because the physical laws governing it are the same throughout the observable universe, because nuclear fusion obeys the same rules in stars billions of light-years away from us, because the spectra of elements have the same lines regardless of where the atom was created. Surprising because within these invariant laws emerge structures and behaviors no simple calculation could predict, because the interaction of individually well-understood processes produces a system whose collective behavior continues revealing novelties. Surprise is not the opposite of comprehension in this context. It is the product of comprehension taken seriously. The more we understand the individual mechanisms, the more clearly we see the complexity they generate together. Nuclear fusion in the core of a massive star is well understood. The convection mixing the internal layers too. The gravitational collapse of the exhausted core likewise. But the dynamic interaction of all these processes during the final moments of a massive star's life still has dimensions, surprising the most advanced computational models. Three-dimensional core collapse simulations, run on the most powerful supercomputers available, continue producing results diverging from model to model in important aspects, especially in the precise mechanism by which the shockwave manages to revitalize and explode the star instead of being swallowed again by the collapsing core. The core collapse supernova explosion problem is one of the deepest open problems in astrophysics. The general theory is well established. The core collapses, forms a neutron star. The implosion energy must somehow be transferred to the outer layers to expel them. The energy transfer mechanism involves neutrinos, convection, hydrodynamic instabilities, and perhaps processes related to the rotation and magnetic field of the nascent core. But the precision with which these mechanisms interact, the exact sequence of events separating a successful explosion from a direct collapse into a black hole without an observable explosion, this remains in the domain of the investigated and not the resolved. Observations of real supernovae provide constraints, but we do not observe the interior of the collapsing core. We only see the light and neutrinos managing to escape, and interpreting both requires models whose uncertainties propagate in complex ways. In this border region, where the known and the unknown touch, there is a particular beauty difficult to articulate but easy to feel when contemplating the data. When a neutrino detector registers a signal from a supernova, as happened with supernova 1987A in the Large Magellanic Cloud, and researchers compare that signal with model predictions, they find an agreement that is reassuring overall and disturbing in the details. The total number of detected neutrinos agrees with predictions within uncertainty margins. The pulse duration agrees, but the fine details of the neutrino energy distribution, which potentially carry information about the temperature and density of the newly formed protoneutron star's interior, were not sufficient to discriminate between competing models with the precision physicists would like. The universe was generous in confirming the general picture. It was less generous with the details. This is precisely what one would expect from a system operating on so many scales simultaneously. On the scale of fractions of a second, the core collapse and shockwave bounce. On the scale of seconds to hours, the shockwave propagation through the star's outer layers. On the scale of days and weeks, the growth of the supernova's brightness as the radioactivity of newly synthesized nuclei heats the expanding material. On the scale of centuries and millennia, the remnant's evolution. On the scale of tens of millions of years, the dispersion of elements into the interstellar medium. On the scale of hundreds of millions of years, the incorporation of these elements into new stellar and planetary generations. Each timescale has its own dominant processes, its own characteristic instabilities, its own forms of regularity and surprise. What is true for the timescale is also true for the spatial scale. The nuclear processes creating the elements occur in a star's core, which has a radius of a few thousand kilometers in the case of a red supergiant, or a few kilometers in the case of a newly formed neutron star. The created elements are distributed by a remnant growing to tens of light years in diameter. These elements then spread through an interstellar medium region hundreds of light years across. Then they gather again in molecular clouds tens of light years wide, and finally collapse into stellar systems with dimensions of fractions of a light year. From the kilometer to the light year and back to the kilometer, the material travels this journey of scales over hundreds of millions of years, and each stage of the journey is governed by different physics and different processes, but all connected in the long chain of cause and consequence that is the galaxy's chemical evolution. Contemplating this chain with patience is realizing the universe wastes nothing. Every atom a star synthesizes goes somewhere. Every photon a supernova emits travels indefinitely until finding something to absorb it. Every shock wave propagating in the interstellar medium compresses and heats and leaves marks lasting much longer than the wave itself. Physics conserves everything, transforms everything, redistributes everything. The universe's entropy increases as it must, but within this general increase of disorder, there are islands of increasing order, regions where gravity gathered what the explosion dispersed. where nuclear fusion reprocessed what had been dispersed, where chemical complexity increased with each cycle of stellar formation and destruction. And, as this cycle advanced over the roughly 13,800,000,000 years since the Big Bang, the variety of elements available in the universe increased. The primordial universe had mainly hydrogen and helium, with traces of lithium. Each generation of stars added carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, argon, calcium, iron, and dozens of other elements in growing concentrations. The universe became chemically richer. The possibility of organic chemistry, of complex molecules, of rocky planets with oceans and atmospheres increased with each cycle. We are the direct product of this historical accumulation. The iron in our blood is older than the solar system. The oxygen in our breath was synthesized in stars that died before the sun was born. The calcium in our bones traversed the violence of at least one supernova explosion before existing inside a living being. This knowledge is not distant or abstract when we let it rest completely. It changes the texture of ordinary perception. The air entering the lungs is the same material that filled the core of a dying star. The dust on windows and roads is composed of atoms that traveled through molecular clouds at tens of degrees above absolute zero before being gathered here. The planet we inhabit is literally formed by the remains of stars that no longer exist. The entire surface, the entire ocean, the entire atmosphere, all life, is stellar material temporarily visiting a particular configuration. In this perspective, the silence of the night is not empty. It is full of a story this narrative has tried to traverse carefully, advancing from process to process, from scale to scale, from moment to moment. But there is still a dimension of this story that has not been fully touched, a perspective that is not about individual processes or cycles or timescales, but about the pattern uniting all this into something that is, in its deepest structure, surprisingly simple. We do not refer to a simplicity erasing the richness of what was described, but to a principle sustaining it, emerging when looking at everything from a certain distance, when the details of individual processes recede, and what remains is the general shape of the entire system. This shape, this unifying principle, is present in every supernova explosion, in every molecular cloud collapse, in every nuclear synthesis inside a stellar core. It is present in the way the galaxy recycles its material through generations of stars. It is present in the relationship between the local chaos of an explosion and the emergent order of a new generation of worlds. It is not something hidden for being mysterious or requiring impenetrable mathematics. It is something hidden simply because it requires patience to see, the patience to contemplate the entire system instead of one of its parts, to let individual processes dissolve slightly into the background, while the pattern connecting them comes forward gently. This pattern emerging when looking with enough distance is not a philosophical abstraction without practical consequences. It has a structure, an internal logic repeating on different scales, and which, once recognized, reveals the cosmos as something much more coherent than the accidental sum of its events. To arrive at this logic, one must observe how the processes we described throughout this journey feed back into each other. How each stage not only follows the previous one, but also modifies it, prepares it, makes it possible in ways only becoming visible when contemplating the complete cycle. The first fundamental feedback is the one existing between the chemical composition of one generation of stars and the composition of the next. When the first wave of massive stars, born almost exclusively from primordial hydrogen and helium, exploded as supernovae and released their newly synthesized nuclei into the interstellar medium, it did not just enrich the surrounding gas. It changed the conditions within which the next generation would form. A gas containing carbon, oxygen, silicon, and iron cools differently from a pure hydrogen gas. Carbon and oxygen, in particular, form molecules like carbon monoxide radiating energy with great efficiency, allowing molecular clouds to lose heat more rapidly and collapse under their own gravity into smaller, denser fragments. This means subsequent generations of stars were not just born from more metal-rich material. They were born in slightly different conditions, with a slightly different mass distribution, with the possibility of forming more complex planetary systems from the start. The nucleosynthesis of first-generation stars did not just produce elements. It modified the very environment where element production would continue, making this environment progressively more favorable to chemical complexity. This is an amplifying feedback, a cycle where each iteration produces richer conditions for the next iteration. But the universe also possesses stabilizing feedbacks, mechanisms preventing cycles from accelerating indefinitely until total collapse or dispersion. The most elegant of these stabilizing feedbacks operates within the stars themselves, at the heart of the fusion processes sustaining nucleosynthesis. A star like the Sun exists in a dynamic equilibrium between the radiation and gas pressure generated by nuclear fusion in its core and the gravity pulling all its material toward the center. When the fusion rate increases slightly due to some fluctuation, the core heats, expands, and this expansion reduces density and temperature, which in turn reduces the fusion rate until equilibrium is restored. It is a cosmic thermostat, an elegant negative feedback keeping stars shining stably for billions of years, ensuring element synthesis occurs sustainably and not in a chaotic explosion consuming fuel in instants. This stability is not trivial. It is what allows stars like the Sun to exist long enough for planets around them to develop complex chemistry, atmospheres, oceans, and eventually conditions, allowing organic molecules to organize into structures capable of replicating. The stabilizing feedback within stars is, in a way, the silent condition making possible all the complexity emerging in their vicinity. There is yet a third category of feedback, less obvious but equally profound, operating on the scale of entire galaxies. The most massive stars, those producing the heaviest elements and ending their lives in supernova explosions, are also the ones most disturbing the interstellar medium around them. Their powerful stellar winds and final explosions compress adjacent gas clouds, potentially triggering new star formation episodes, or else dispersing the gas and temporarily inhibiting gravitational collapse in nearby regions. The galaxy, therefore, is not a passive system where stars simply are born, live, and die in orderly sequence. It is a system where stars actively regulate the pace of their own birth, where the death of one star can both create and destroy conditions for the birth of others. Nucleosynthesis, seen from this perspective, is not just chemistry, it is ecology. A cosmic ecology where producers, consumers, and decomposers are different types of stars and stellar processes, and where the entire system's equilibrium depends on interactions between them. To appreciate the deepest dimension of what happens when a star synthesizes elements, it is useful to descend from the stellar scale to the nuclear scale to the inner world of protons and neutrons composing atomic nuclei. Every element existing is defined by a specific number of protons in its nucleus. Hydrogen has 1, helium has 2, carbon has 6, iron has 26, gold has 79, uranium has 92. This proton count is the most fundamental identity of an atom, the property determining which electrons it can accommodate, which chemical bonds it can form, which role it will play in the theater of chemistry. When a star fuses hydrogen into helium, it is literally transforming one identity into another, converting one type of chemical being into a different type of chemical being, and doing so with an efficiency and scale ordinary chemistry could never achieve. What governs which nuclei can exist and which cannot is the competition between two fundamental forces: the electromagnetic force, pushing positive protons away from each other, and the strong nuclear force, attracting protons and neutrons to each other at very short distances. For each number of protons, there is a range of neutron numbers resulting in stable nuclei. Outside this range, nuclei are radioactive and spontaneously transform into other nuclei through decay processes. The map of all possible nuclei, stable and unstable, is called the chart of Nuclides, and it has a shape reflecting the depths of nuclear physics. The valley of stability running through this chart, where the most stable nuclei reside, is the terrain stellar nucleosynthesis systematically explores, advancing along the valley as increasing temperatures and pressures allow progressively more difficult fusions. Iron and nickel occupy the lowest point of this stability valley, the configuration where nuclei have the highest binding energy per particle, where the strong nuclear force extracts the maximum possible cohesion from the arrangement of protons and neutrons. This is why stellar nucleosynthesis advances toward iron and stops there as far as fusion is concerned. Going beyond iron through fusion does not release energy. It consumes energy, and a star attempting to fuse iron would only accelerate its own collapse. The production of elements heavier than iron therefore requires a different mechanism, and nature found not one but several different mechanisms, each operating under specific conditions and contributing a specific set of elements to the periodic table. The slow neutron capture process, occurring in asymptotic giant branch stars at the end of their lives, patiently builds elements like barium, cerium, neodymium, and lead over millions of years, adding neutrons one by one and waiting for radioactive decays, readjusting the proton number. The rapid neutron capture process, occurring in environments of extraordinarily high neutron density like core collapse supernova or neutron star mergers, builds even heavier elements in fractions of a second, adding dozens of neutrons before any decay can occur. Each of these processes leaves a compositional signature, a characteristic ratio between different isotopes astronomers can detect in the spectra of ancient stars and in the abundance patterns of primitive meteorites. Nucleosynthesis did not just produce the elements, it marked them with a history that can be read, with patience and sophisticated instrumentation, as if they were growth rings in a cosmic tree. The molecular dimension of this story is where the chemistry of elements meets the biology of life in a way still causing wonder in those who pause to contemplate it attentively. Carbon, synthesized inside low and intermediate mass stars through the triple alpha process, has a unique property among all elements. It forms stable covalent bonds with itself in the chains of practically unlimited length, and forms these chains in combination with hydrogen, oxygen, nitrogen, phosphorus, and sulfur, with a diversity of geometries and properties unmatched in any other chemistry. This property is not accidental in the sense of being arbitrary, It emerges directly from carbon's electronic structure, which in turn emerges from the number of protons in its nucleus, which in turn emerges from the specific nucleosynthesis process that produced it. Carbon-based life is, ultimately, a consequence of the nuclear physics of triple alpha fusion in stars with specific masses. Oxygen, produced by the fusion of helium and carbon inside the same stars and in massive stars before their explosions, is the most abundant element in Earth's crust, and the third most abundant in the universe after hydrogen and helium. It forms with hydrogen water, the universal solvent making life's chemistry possible by dissolving ionic compounds, participating in enzymatic reactions, moderating temperatures. It forms with silicon, the silicates composing most of the rocks of terrestrial planets, creating the solid surface upon which life can develop. It forms with carbon functional groups like hydroxyls, carbonyls, and carboxyls, giving organic molecules their diversity of chemical reactivity. Each of these functions of oxygen in the chemistry of life and planets is, ultimately, a consequence of having 26 electrons distributed around a nucleus with 8 protons, a configuration which in turn is the product of nuclear processes occurring in stars that existed long before the Sun. Nitrogen, produced mainly by the CNO cycle in the most massive stars and by the carbon-burning process, is the main component of Earth's atmosphere and an essential constituent of all amino acids and nitrogenous bases of DNA and RNA. Phosphorus, forged in advanced burning stages in massive stars and dispersed by supernovae, forms the backbone of the DNA double helix, the phosphate groups connecting nucleotides and carrying metabolic energy in ATP molecules. Sulfur, equally a product of advanced stellar nucleosynthesis, forms the disulfide bridges maintaining the three-dimensional structure of proteins. Every element composing a living being has a stellar address, a traceable origin in nuclear processes occurring in specific stars at specific moments in galactic history. Contemplating the system as a whole, what emerges is a vision of extraordinary coherence. The universe began with hydrogen, helium, and traces of lithium, the simple heritage of the Big Bang. The first stars took this simple material and processed it, forging light elements in their cores and heavy elements in their final explosions, and returned everything to the enriched interstellar medium. This enriched material formed the second generation of stars, which repeated the process with variations, adding more metals, altering formation conditions, creating more complex planetary systems. The galaxy repeated this cycle through billions of years, each generation building on the chemical heritage of the previous ones, each supernova explosion being both an end and a beginning, both a dispersion and a sowing. The complex patterns we see, the entire periodic table with its 92 natural elements, each with its specific properties, each with its isotope distribution, each with its role in the chemistry of life or rocks or stars, all these patterns emerge from a surprisingly simple set of rules. Gravity collapses gas clouds. Increasing pressure and temperature allow specific nuclear fusions. Nuclear stability defines which fusions release energy and which consume it. The competition between gravity and radiation pressure regulates the pace of synthesis. Final instabilities result in explosions dispersing the product. Gravity gathers the dispersed material again. These few rules, repeated through countless stars and billions of years, produced all the chemical complexity of the cosmos. Deep down, The stellar creation of elements is simply the universe developing its own complexity from the inside out, using the most fundamental laws of nuclear and gravitational physics to transform the initial uniformity of the primordial plasma into the differentiated richness of the periodic table, creating through cycles of stellar birth, fusion, and death the ingredients of everything that exists, from rocks to oceans, from proteins to planets, from neurons to galaxies. Every stellar furnace we described, from the quiet core of the sun burning hydrogen into helium over billions of years, to the rapid cascades of carbon and oxygen and silicon burning in massive stars in their final years, to the dizzying collisions of neutron stars forging gold and platinum in instants. All these furnaces are different expressions of the same principle. The universe using gravity to create the pressure and temperature conditions allowing the most fundamental blocks of matter to reorganize into progressively more complex and stable configurations. The slow neutron capture process in red giants and the rapid process in supernovae are variations on the same theme, different rhythms in the same composition. The nuclear burning chain in massive stars, from hydrogen to helium to carbon to neon to oxygen to silicon to iron, is a scale of increasing complexity, each note harder to play and richer in consequences than the previous one. Element synthesis is not just chemistry. It is the way the universe keeps memory of its own history. Every iron atom in your blood is a fossil of a supernova that occurred before the sun existed. Every calcium atom in your bones was forged in a furnace that no longer exists. Every carbon atom in your DNA molecules was synthesized in some red giant that ended its life dispersing its outer layers into a planetary nebula. You are a library of nuclear events, a chemical archive of billions of years of stellar history, compressed into a form that breathes and thinks and feels. And while you rest now, this process continues. Somewhere in the galaxy, a molecular cloud is collapsing under its own gravity, heating at its center, about to ignite the flame of a new star. Elsewhere, a red giant is in its final millennia, patiently beating its elements into the stellar wind that will carry them through space. Elsewhere still, a massive star is in the final hours of its life, burning silicon into iron in its core with growing urgency, advancing toward the collapse that will result in an explosion illuminating its galaxy for weeks. These events do not depend on your attention to happen. They occur with the same serenity they occurred for billions of years before you existed, and will continue for billions of years after. There is something deeply reassuring in this vastness of process requiring no supervision from you, happening with precision and regularity, regardless of what happens in any small corner of the cosmos. You are safe. While stars are born and die on unimaginable timescales, you are here now, at rest, in safety. The universe cares for you in a way that is not metaphorical. It literally created the atoms composing your body, forged them in stellar furnaces over billions of years, dispersed them through space, gathered them on a planet around a stable star, and waited patiently while chemistry and biology organized them into a form capable of contemplating its own origin. Everything is in order. The order is not the rigid order of something static and motionless, but the fluid order of a system maintaining coherence through cycles and transformations. The order of a river constantly changing but remaining a river. The order of a flame consuming and renewing but remaining a flame. While you rest, the stars continue their silent synthesis. In their cores, protons fuse in groups of 4 to form helium, releasing the light that will cross space for years before touching the surface of some planet. In the entrails of red giants, the triple alpha process transforms helium into carbon, with the patience knowing no rush. In the accretion disks around neutron stars in binaries, the rapid process forges gold and platinum in instants of extreme density. All this happens while you breathe slowly, while your body relaxes, while your thoughts soften and lose their sharp contours. You are part of this. You always have been. Not in a sentimental or vague way, but in a precise and verifiable way. The atoms you carry have stories stretching across billions of years, passing through stars, through empty space, through molecular clouds, through planets, through oceans, through life forms prior to yours, until reaching you, now, in this moment of rest. You are the temporary arrival point of a chain of processes that began in the twilight of the first generation of stars. And when you exhale your last breath, much further ahead, these atoms will continue their journey, dissolving back into the chain of transformations awaiting them. For now, they rest in you. For now, you carry them, and you also rest. The process continues effortlessly. Fusion happens without tension. Stars shine without urgency. The universe unfolds with a calm traversing billions of years without being disturbed. Let your thoughts become like nebulae, vast and soft, and without defined contours. Let your breath become like stellar wind, gentle and constant, and without a particular destination. Let your body sink into rest like a molecular cloud sinks into its own gravitational collapse, softly, inevitably, towards something new. You are safe. The universe cares for you. The stars are in their places. The galaxy turns gently. The elements you carry were made with care over a time the mind cannot truly embrace, only revere. You are made of ancient and beautiful things. You deserve to rest. Good night. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.